To complete this class on derivatives of exponential and logarithmic functions, we're going to have a look at this very powerful technique called logarithmic differentiation. It is a method, and so it will consist of several steps, but it uses pretty much everything we've seen so far, just puts it all together. To introduce this method, let me show you what prompted its development. So let's say that we need to find the derivative of a function that looks like that. So it's a function that has the x both in the base and the exponent of a power. So we cannot use the power rule because the power rule requires the exponent to be a constant, and in this case the exponent is not constant. And we cannot use the exponential rule either because the exponential rule requires the base to be a constant. In this case, the base is f of x, which is not a constant. So what are we going to do? The way it is right now, we cannot use any of the rules that we have seen so far. But what we can do is we can get rid of this strange combination by applying logarithms. Remember, one of the properties of logarithms is that by applying logarithms we can actually move an exponent down into a coefficient position. So in other words, if I apply logarithms on both sides, I end up that ln of y is equal to ln of f of x to the power g of x, and then now I can take the g of x down. And so now notice that the problem that has stuck up to a minute ago has disappeared. We don't have anymore a power with the x both in the base and the exponent. So all we need to do right now is differentiate both sides implicitly, which is something that we can do and we're going to do in a minute. But before I do that, let me tell you that this is exactly what is the method called logarithmic differentiation. So the idea is when we're dealing with a function that cannot be differentiated in other ways because of some complication in the formula, or sometimes that it can be, we'll see in a minute, in a situation where the function could be differentiated as is, but by using logarithms, applying logarithms, and using properties of logarithms, we can make the differentiation possible, as in this case, or easier, as in the case we're going to see later. So let's complete this derivative of y equal f of x to the power g of x. All right, so what we said is we're going to apply the logarithm. This brings us to a point where we know that ln y is equal to g of x times ln of f of x. And now what we need to do is apply the product rule and the chain rule. So on the left hand side, we apply the chain rule. And so that gives us the derivative of ln y is 1 over y times the derivative of the inside, which is y prime, gives us y prime over y. On the right hand side, we'll do the first function times the derivative of the second. This will give us g of x times the derivative of ln of f of x, which is 1 over f, times the derivative of f, which is f prime. Then of course we're still working with the product rule. Now we have to take the derivative of g and multiply it by ln. Well, the derivative of g is just g prime, so it ends up being g prime ln f. Okay, so at this point we move the y to the other side. Remember, y was f to the power g, and we have this complicated expression, and just for the sake of it, well, not really, there is a reason, I'm going to multiply everything out to FOIL it. Okay, so notice that we end up with g times f to the power g minus 1 coming from that f in the denominator times f prime plus g prime times f to the power g times ln f. Now this may look like a complicated formula, and in a way it is, but let's look at what it is made up of. Let's look at this first term. That's g times f of g to minus 1 times f prime. Well, if you think about it, this is what we would have gotten if we had applied just the power and the chain rule to the original function, assuming that g was constant, right? We would apply the power rule, that would give us g f to the g minus 1, and then multiply by the derivative of f. On the other hand, if we look at this second piece, that is what we would have gotten if we had taken the derivative of this function by assuming f constant and therefore applying the exponential and the chain rule. So if we apply the exponential rule, then we end up with f to the power g times the derivative times the ln of f times the derivative of g. So what we have is that in this particular situation, the derivative is obtained by using two rules, or using two methods under two different conditions. One, assuming that the exponent is constant, the other is assuming that the base is constant. And so that's an interesting thing that goes under the name of the POW-X rule, for power and exponential all combined. If you prefer to memorize this rule, that's fine. If you remember to simply apply the logarithmic differentiation every time you use it, that's also pretty fine.